Hi, my name is Frank Trusdell. I'm a geologist with the U.S. Geological Survey's Hawaiian Volcano Observatory, and today my presentation will be about the current status of Mauna Loa volcano. This talk will be broken down into several different parts. The first part will be a general overview of Mauna Loa. Mauna Loa is the world's largest active volcano, and the surface area of Mauna Loa comprises over 51% of the island of Hawaii. By itself, the landmass that Mauna Loa encompasses is almost equal to twice all the other Hawaiian islands put together. When speaking about volcanoes and volcanic hazards, it's important to know the structure of Mauna Loa and where lava can emanate from the volcano and impact communities downslope. The summit area of Mauna Loa is represented by these blue colors, which represent eruptive fissures. The top of the volcano is capped by the summit caldera Mokuaweoweo, and trending away from the summit of the mountain are two rift zones. To the northeast, shown in red, are eruptive fissures from the northeast rift zone. And then to the southwest are fissures shown in magenta that extend all the way down to South Point. And Mauna Loa has a class of radial vents that are unique amongst Hawaiian volcanoes, which we call radial vents. And they are shown here by these brick red colors. Now, radial vents are unique in that their activity is not confined to the summit or to the rift zones. They can break out away, radiating away from the caldera in a north, a northwest, or a westerly direction. Just like bicycle spokes radiate away from the hub, imagine Mokuaweoweo is the hub, and these radial vents are the spokes to a wheel radiating away from the hub. Now, radial vents are different in that they can break out below sea level. In 2002, we had an oceanographic cruise where we were able to map 11 radial vents off the coast here from Kealakekua down to Ho'okena. So they can occur below sea level all the way up to the summit caldera at 13,000 plus feet. So they can happen at all elevations, and that has implications for volcanic hazards. We're going to look at the history of Mauna Loa and where and how frequently different geographic sectors have effused lava. The summit caldera of Mauna Loa has been responsible for about 50% of all eruptions. And what I mean by that is that an eruption will start in the summit area, and the entire eruption will last in the summit area. And typically, eruptions in the summit, when the caldera fills up, it spills out flows preferentially to the north and towards the south. And these flows have gone out to 10 to 15 kilometers away from the caldera. So usually these eruptions do not pose a threat to the communities on the flanks. Northeast Rift Zone has been responsible for about 25% of the eruptions. So eruptions start the summit in a northeast rift zone eruption. An eruption will start in the summit, and then the dike will propagate down into the northeast rift zone. And then a lower elevation site will become the dominant place of lava effusion, and this will send lava flows downslope. And most of the historical eruptions in the past have sent lava flows in a northerly direction, and following the natural drainage between Mauna Loa and Mauna Kea, they end up turning in the direction toward Hilo. The 1984 is outlined in my pointer here and got within about 4 miles of Kaumana City. Southwest Rift Zone has been responsible for about 20% of the eruptions. And the eruptions have occurred along the entire length of the rift zone, and eruptions have spilt lava both to the west and east side of the rift zones. The most recent eruption from 1950 is shown in this magenta color here, and has spilt 3 independent lava flows from the rift zone towards the South Kona coast. There have been 3 historical radial vent eruptions. The most obvious one is this one here shown on the northwest flank from the 1859 eruption. This eruption started at about 11,000 feet, went around the north side of Hualalai volcano, and entered the ocean at Kiholo Bay. There was another eruption in 1852. A dike propagated to the north of the caldera and effused lava that went in this general direction and is represented by this orange flow. In 1877, there was a radial vent eruption in Kealakekua Bay. So this was a submarine eruption. It had a summit phase. The dike propagated, people felt earthquakes. And then there was an outbreak underwater that sent up floating, glowing rocks. There was sulfur smell and discoloration and some dead fish. So let's look at eruption rates and how this may differ from Kilauea volcano. This is a slope map showing the degree of slope across the island of Hawaii. The warmer the colors, the steeper the slope. So you can see in the upper reaches of Mauna Kea volcano, it's very steep, and thus it has these deep orange colors to it. So looking at Mauna Loa, just adjacent to the caldera, we have very steep slopes. Down in the South Kona area, we have very steep slopes. These large numbers shown here are the average effusion rates for the entire eruption in millions of cubic meters per day. So let's start with the highest region. At 12 million cubic meter per day average effusion rate along the southwest rift zone of Mauna Loa, you can see that we have a combination of high effusion rates and steep slopes resulting in transit times of lava flows from their vents to the ocean in a matter of hours. So in the previous slide, I pointed out there were these 1950 flows, 3 of them. First one reached in about 3 hours. The next one reached the ocean in about 14.5 hours. And the last one, the Ka'apuna flow, reached the ocean in 18 hours. In 1919, the lava flow took about 1 day from its source vent to reach the ocean. The one anomaly along this entire coastline is this of 4 days, which is the 1926 eruption. This eruption happened to break out right along the ridge crest and sent flows in both directions. So the initial volume had to be split into 2 independent lobes, and this decreased the availability of lava and thus the speed at which the lava flow could advance towards the coastline. To the south, adjacent to Hawaiian Ocean View Estates, is the 1887 lava. This reached the coast in just over a day at 29 hours. And then next to the Kahuku Fault Scarp is the 1868 lava, and this reached the ocean in about 3.5 hours. Going to the next highest diffusion rate area, about half of that of the southwest rift zone, is the northeast rift zone at 6 million cubic meters per day. Now this area, if you look at the topography, the slopes are much more gentle. You see mostly yellows, and in fact, in this area here, you see greens. So the tendency is to have a summit breakout, the dike propagates. It has an area in which the vent localizes and becomes a dominant emitter of lava. And then the flows rush away from the rift zone. And in this high area in the saddle, what I call the intermontane area, are gentle slopes. So the topography then, so the vents go down to the shallow topographic area. And those of you who have watched lava during the Pu'uo'o eruptive series, what you see is lava move down the high or the steep slope areas rapidly. And then when they hit the coastal plain, in this area, the high intermontane area, because the slopes are gentle, the flow front actually slows down and starts to spread apart. And yet magma supply from the source area just keeps rushing down the slope. So what happens is you create an area in which the front isn't advancing rapidly enough for the supply, and so you'll have an initial lobe reach out, and then you'll have a logjam situation at the inflection point between high and low slopes. The lava then will jump out and make a secondary flow and a tertiary flow. And this is what happened in 1984. It also happened in 1880, the initial part, and then 1855, and then 1843 and 1935. Ultimately, the 1880 lava flow localized to a singular vent. It formed the tube system. Because it was a long-lived eruption, it slowly worked its way all the way down here, where it reached the outskirts of Hilo at the time, and now is found at the distal end of this flow between Kilauea and Kinaole streets. I'm sorry, that's Kilauea and Komohana streets. So the tip of this is between those two, and it took over 200 days to reach the coastline. We only have one event in which it's well documented for a radial vent eruption, and the average effusion rate there was 3 million cubic meters per day. But the initial phase of A'a was probably much closer to the southwest rift zone diffusion rate, where the initial flow to reach the coastline down here in 8 days was A'a, and the Pahoehoe phase took over 100 days ultimately to reach the coastline. So let's look at the current status of the volcano. This slide shows all of the monitoring equipment that we have island-wide for monitoring the volcanoes on the island of Hawaii. The different symbols represent the different types of instrumentation that we have. And for Mauna Loa specifically, we have over 24 GPS stations, 17 seismic, 7 tilt meters, strain meters, gas sensors. We have, right now, we've actually upgraded this so that we have 6 webcams and 1 infrasound system. And that's specific to Mauna Loa, and yet the regional sensors can also inform us about potential activity at the volcano. Now let's look at an idealized volcanic monitoring system and how we would monitor the volcano. So this cartoon is showing us essentially a volcano at rest. And since we're fed from the Hawaiian hotspot, there seems to be a constant trickle of magma into the volcanoes. So as this trickle starts to come into the subsurface magma reservoir, the reservoir begins to swell. So we have our instruments across the flank of the volcano, and we're trying to monitor volcanic activity. So as the influx of magma increases and the magma reservoir starts to swell, the first thing we notice are change in our deformation monitoring. So as the magma comes in and the reservoir starts to fill and pressurize, it causes changes in the landscape. So this dashed line represents the elevation of the volcano when the volcano was at rest. And now we see that the volcano is starting to swell. So we have uplift of the volcano, and we can see that in our GPS sensors. We also have our tilt meter starts to increase with greater ingress of magma. And then horizontal distances between 2 points along the caldera and between 2 points along the flank also start to increase. And as the magma reservoir starts to fill, then the next thing we start to see is a sequence of earthquakes as the rocks around the magma reservoir is starting to become stressed. Ultimately, if the pressure is great enough, that will drive an eruption. Sometimes eruption will occur, like it is currently in 2021, right up here in the summit. Or, as in the case in 2018, there was a flank outbreak and lava started to evacuate the main magma reservoir. We could track the movement of the dike down the flank through a series of earthquakes, and also by having changes in GPS and other deformation monitors along the flank. At the summit, as the lava evacuated the main magma reservoir, we start to see a decrease in elevation, a contraction of the lines across, and ultimately the tilt meters then return or show a decrease or a deflationary trend. So keeping in mind that simple cartoon, we will start to look at the seismicity that preceded the eruptions in 1975 and 1984. Precursory seismicity before the 1975 eruption, there were populations of earthquakes that occurred. The mid-level or the mid-depth earthquakes at 5 to 13 kilometer depths happened on the northwest flank of the volcano. And this was an early indication that magma was on the move. And as this population of earthquakes started to increase, progressively seismicity then moved to the shallow edifice around Mokuaweaweo, the South Caldera region, and the upper Southwest Rift Zone. Preceding the eruption in 1984 was a same pattern of mid-level earthquakes in the Northwest region, progressively seismicity shallowing to the summit caldera and the South Caldera region and the upper portion of the Southwest Rift Zone. And all of these magnitudes I'm showing here are greater than 1.6. If we were to show all the magnitudes of the earthquakes, you could take the population that you see on each slide and roughly times it by 5. So for all earthquakes, there would be 5 times more dots on this map. Seismicity leading up to the 1975 eruption is shown here with the number of earthquakes per day over the timeline on the x-axis. So you could see that seismicity ramped up fairly quickly, where over a period of time of quiescence or background, as Mauna Loa started to reawakening, we had few hundreds of earthquakes per day. And prior to the eruption, there were a few days where the earthquake counts on a daily basis exceeded 1,000 earthquakes. And just prior to the outbreak, you could see we were in the mid-hundreds of earthquakes, between 3 to maybe 600 or 700 earthquakes on a daily basis. Seismicity leading up to the 1984 eruption is shown in this plot, and this is shown as hourly counts in the month of March, leading up from March 15th all the way up to the outbreak shown in this arrow. But the activity increased from bursts of earthquakes, intermittent activity, to a steady stream of earthquakes, with many hundreds of earthquakes sustained for weeks prior to the outbreak. So this plot shows both of those precursory seismicity for the 1975 and the 1984 eruptions, with the number of events shown here and a timeline across. Shallow seismicity is represented by the blue line. Intermediate seismicity is represented by the red line. And you can see that the intermediate seismicity started to ramp up, and then the shallow seismicity, and both of them in unison, ramped up quite rapidly until the eruption happened. And as I stated before, these were many hundreds of events on a per day scale. After the 1975 eruption, seismicity kind of went along relatively slowly, and then intermediate seismicity started to pick up. The shallow seismicity in correspondence also picked up. Then the intermediate seismicity picked up quite dramatically, resulting in a steeper increase in shallow seismicity until the eruption occurred. Now, what does the seismicity look like now? Here's a plot of Mauna Loa. Here are the earthquakes in the northwesterly sector. And those that are in orange are earthquakes that represent the same orange in the prior two plots. These are the intermediate depth earthquakes. So orange and yellow are the intermediate depth on this plot. And the shallow earthquakes, instead of being green on this plot, are represented by the red dots. So here's the summit caldera. Here's the south caldera, Mauna Loa, and then the upper southwest rift zone. And so the seismicity is starting to look very similar to what preceded the eruptive activity in 1975 and 1984. If we look at earthquake counts now, over the last 2 years, we see that we have bins of earthquakes, and these are binned by the week. So you can see the blue lines represent earthquakes per week, and there were periods of time where we went relatively high, and then we've gone back down to below 100 per week, and then we go up to 100 per week, and sometimes exceed, kind of come back down. And so we're kind of going up and down, but these are in earthquakes per week, not earthquakes per day. So this is the kind of plot that we would expect to see, and if it was earthquakes per day, then we're kind of in the same range as prior to 1984. Here is the plot by earthquakes per day, and you can see that sometimes we get up to in the hundreds, but mostly you can see the earthquakes. If you were to kind of do a best fit line, we're still relatively below 50 earthquakes per day. And the most recent period, we're actually down in seismicity. So far, even though the activity looks fairly active at the summit, the earthquake counts aren't quite up to the same types of numbers that we saw prior to 1975, 1984. Now here's a plot of the precursory seismicity in 75. Here's a plot of precursory seismicity prior to the 84 eruption. And here's the current seismicity. And like I said, these look relatively the same. Now, there's an important point to make about this magnitude greater than 1.6. Since 1984, we have increased the number of seismic stations across Mauna Loa, but we also have increased the the quality of the instruments that we are using. So the sensitivity of those instruments are much greater than the equipment that was used to note the seismicity prior to that period of time. And in order to compare more appropriately the current seismicity to the old school seismicity, we have to use a cutoff of 1.6 because these instruments weren't as good as detecting the smallest magnitude events, and current seismometers are way better at that. So if we compared all magnitude events, this right-hand side plot would be like a bee's nest, just blanketed with materials of magnitudes even and including less than 1. Now, the reason why I put this gray bar here, for those who might be wondering, is to make these plots comparable in terms of where the seismicity is. So this cutoff is equal to the bottom of both of the prior epochs of time. Now let's look at deformation. This plot represents 3 years of GPS data from Mauna Loa. So here's the summit caldera. At the base of each of these arrows is a GPS station. And the plot here is showing the velocity, the movement of these stations or the flank in response to ingress of magma within the storage edifices within the volcano. So we have a nice relatively radial pattern, which would suggest that there is an area underneath this portion of the flank of the volcano that has magma accumulating in it. And in response, the flank is moving up, but is also moving out. The one thing you'll notice is that these vectors on the east side are larger than those on the west side. Okay, let's look at a different period of time. If we look at just 1 year ago, we still have GPS data over the past year. We basically have the same portion of the flank showing accumulation of magma. We have this nice radial pattern around the flank of the volcano showing that accumulation of magma. And yet those facing the Kilauea side or on the eastern flank of Mauna Loa are still moving at a faster rate than those on the west side. Let's look at 6 months ago. Over the last 6 months, seems to be a little bit more equity, same inflationary center. And looking at this vector compared to these vectors, they seem to be moving almost, well, they seem to be of the same relative scale or size. Although these vectors here and this one here are still shorter than both of these or all three of these on this side. So one is showing a comparable rate of motion or velocity, I should say. Now looking at 3 months ago, look at 3 months. Still, we have this radial pattern. It looks like possibly that it moved a little bit further north because these arrows are pointing down instead of away. And maybe there's a possible shift of inflationary center to the northern part of the caldera. And then we'll look at the last month. And if we look at the last month, because it's a shorter baseline, we expect the arrows to be shorter. And this pattern of this side having larger vectors than any other side is still holding up. So this portion of the flank of the volcano is moving more rapidly than the other flank of the volcano on the other side of the caldera. If we look at the INSAR data shows it's a satellite ranging device. So we have a satellite that flies over on March 15th. And then we had another satellite fly over on December 10th. And that was March 15th, 2019 versus December 10th, 2020. And what we do is we take the two images that the satellites captured, and then we subtract one from the other. And down here, you can see the rate of change So if you had a full rate of change, then you had about 1.5 centimeters of change. And in this case, if we start here, we got from one magenta to another magenta color. We basically have one full scale of change. And so we have about 1.5 centimeters of change. If we start at this outer ring, then we had about 3 centimeters of inflation of the volcano. Here's the caldera. So this inflationary center, because we have a butterfly wing pattern, is suggestive of an elongate body inflating across the floor of the caldera. So in summary, what's happening now at Mauna Loa? Well, we have in small degrees of inflation at the summit. We have above background seismicity on the flank. We have slightly above background seismicity in the summit and the upper southwest rift zone, but that's episodic. And what are we missing? We're missing more consistent and persistent seismicity. So instead of having a sawtooth pattern on those daily counts, we'd like to see a gradual ramping up and not have days in which the seismicity drops down to or below 10 earthquakes per day. As I said, in 1975, we were in the multiple hundreds of earthquakes per day. And in 1984, we were between 50 and 100 earthquakes per day. And so we don't have that yet. So we need more consistency and we need more persistent seismicity. In addition, we need to see increasing rates of deformation, a substantial radial pattern, and with increasing rates of deformation, we should also have corresponding increasing rates of seismicity. So what is the Hawaiian Volcano Observatory doing in response to this changes at Mauna Loa? So we have created some inundation maps, and these are meant to be used by emergency managers in case there are outbreaks along the flanks of the volcano. These can be used in a response activity to see what is downslope and potentially in harm's way. And you can view these maps yourself on the website at this URL. Furthermore, we have the steepest line of descent maps, and these can be used also in eruption response. Looking at where the emitting source is, then you can follow potential lava flow paths down to the coastline using the steepest lines of descent. What else is HVO doing? Well, HVO is maintaining and upgrading our monitoring equipment. We're adding new instrumentation as we can and budgets allow. We're doing internal planning for response to an eventual eruption of Mauna Loa. We're coordinating and planning with our partners. Just to name a few: National Park Service, Civil Defense, FEMA, etc. We're evaluating what kind of aviation assets might be available to us to respond to, say, a high elevation eruption on Mauna Loa. There are very few possible helicopters that can carry a crew to such elevations. But we're also investigating whether or not we could use satellite technology or UAV to facilitate our response. We're briefing key agencies, congressional staff, and we're providing community outreach like this Volcano Awareness Month program. We write volcano watches, we have public presentation, community meetings, and a nicely updated website. So what's the take-home message? People should be aware of the hazards. You should stay informed. Mauna Loa is showing signs of reawakening, but an eruption is not imminent. Thank you.